Swayam Prabha. Digital India. Educated India.
Welcome to lecture 7, numerical problem. In this lecture, we will be solving numerical problem based on the vapor compression system with subcooling. This is the numerical question. The evaporator and condenser temperature are same. That is, evaporator temperature is minus 18, condenser temperature is 32. The refrigerant at the exit of the condenser is subcooled to 26 degrees centigrade. Is subcooled to 26 degree centigrade. Mass flow remains the same, 0.05 kg per second. Determine the rate of heat removal from the refrigerator space and power input to the compressor, rate of heat rejection to the environment, and COP of the refrigerator. So, this is the temperature entropy diagram for the ideal vapor compression refrigeration cycle with subcooling, and this is the pH diagram. So, I will be plotting it again. So, we assume the condition of refrigerant at the inlet of compressor is saturated. So, this is, let me draw the pH diagram first. This is 1 to 2 is isentropic compression. This is the work of compression. This is 2 dash. This is 3. So, this is subcooling. Let me represent by dotted line. This is without subcooling, throttling. Without subcooling, 3 to 4. And with subcooling, so this is 3 dash, this is 4 dash. So, this is with subcooling. Evaporator heat load, process 4 to 1, and this is condenser heat load. Let us mark the temperatures. So, this is evaporator temperature TE. This one is condenser temperature. Let me plot the process on a pressure enthalpy diagram. Y-axis is pressure, x-axis is enthalpy. So, this is state point 2, this is 1, this is 2 dash, this is 3, this is 3 to 4 is without subcooling. And this is 3 dash, this is 4 dash. condenser heat rejection, evaporator heat load. This is work of. So let us write the given data. Evaporator temperature minus 18, condenser temperature is 32, and the refrigerant at the exit of the condenser is subcooled to a temperature of 26. So given data, T1 is equal to T4, which is equal to T4 dash minus 18 degrees centigrade. Mass flow rate of refrigerant is given as 0.05 kg per second, and T2 dash equal to T3 equal to condenser temperature, which is equal to 32 degrees centigrade. Refrigerant is subcooled from 32 to 26 degrees centigrade. That means this temperature is 26 degrees centigrade. This is T3 dash. So T3 dash is given 26 degrees centigrade. So the degree of subcooling is the difference in temperature between 3 and 3 dash. The degree of subcooling is T3 minus T3 dash. T3 is nothing but condenser temperature, so which is equal to 32 minus 26, that is equal to 6 degrees centigrade. 6 degree centigrade. So let us solve this problem. So here it is m dot, mass flow rate is m dot. So we will start from state point 1. State 1 is lying on saturated vapors region. So directly we can read the enthalpy and entropy value from the table. Let us start from state point 1. So state point 1 is in saturated vapor. It is a condition of reference. State point 1 is saturated vapor, which is lying on the saturated vapor line. So S1 is equal to Sg, H1 is equal to Hg, which is both these are at temperature, evaporator temperature minus 18 degrees centigrade from R134A table. 134A table. So if you see the values, we'll see S1 is equal to, this is minus 18 degrees centigrade. Sg value is, this is liquid entropy, this is vapor entropy, 1.7399. And vapor enthalpy is 387.89. So H1 equal to 387.89 kilojoule per kg, and entropy value is 1.7399. 1.7399 kilojoule per kg. Kilojoule per kg Kelvin. Yes, that is what I have mentioned here. 387.89 and 1.7399 kilojoule per kg. Now let us move to state point 2 to determine the, again for this problem we don't know the temperature of the refrigerant after the refrigerant is compressed. That is state point 2. T2 is unknown. T2 is unknown. So we need to find out, like how we found for one of the problem in the previous lecture. Okay, so I'll be using this relation S2 minus S2 dash is equal to Cp of vapor into ln of T2 by T2 dash. S2 minus S2 dash is equal to Cp of vapor into ln of T2 by T2 dash. If you see this diagram, this temperature is unknown. Okay, So T2 is not known. Let me write it. T2, this is the temperature T2. That is, we have to determine. T2 is, so this is unknown. S2 minus S2 dash. Now, if you look at the diagram, state point 2 dash is lying on saturated vapor line. So we can directly read the vapor entropy value from the table corresponding to condenser temperature. So now S2 dash is equal to, let this be equation number 1. Equation 1. S2 dash is equal to Sg at T2 dash temperature. What is the temperature of T2 dash? T2 dash is nothing but T3, which is nothing but condenser temperature 32. 32 degree centigrade. From R134A. So if you look at the value, S2 dash is equal to, this is 32. Vapor entropy is here 1.7142. 1.7142. 1.7142 kilojoule per kg Kelvin. Since process 1 to 2 is isentropic, therefore, this is equal to S2. S1 equal to S2. S1 is equal to S2. So, S2 value is nothing but S1, 1.7399 kilojoule per kg Kelvin. Now, substitute values of S2, S2 dash. Before that, I think we have to find out the Cp of vapor. So, let us find the Cp of vapor here. I will use this portion. Since the temperature T2 is unknown, we cannot find out the average of T2 and T2 dash. So, Cp of vapor have to be found out corresponding to the temperature T2 dash. So, Cp of vapor to be found corresponding to the temperature T2 dash. Since T2 is unknown, we cannot find the average. So, T2 dash. What is T2 dash? T2 dash is 32 degrees centigrade. So, Cp value should be taken for this one. Corresponding to 32, Cp of vapor is 1.058. Cp of vapor is equal to 1.058. This is from R1348. From R134A table. Now we can substitute the value of S2, S2 dash, Cp of vapor, T2 dash in equation 1. In equation 1. So if we substitute, we will get S2 is 1.7399, S2 dash 1.7142 equal to Cp is 1.058 into ln of T2 by T2 dash. T2 dash is 32. So we have to convert into Kelvin. So if you solve this one, you will get T2 is equal to, if you solve this, you will get close to 40 degrees centigrade. That is 312.5 Kelvin, 39.5 degrees centigrade. 312.5 Kelvin or 39.5 degree centigrade. 39.5 degree centigrade. So this is the condition. Now we can find the superheated enthalpy. Superheated enthalpy at state 2 because we want to find out H2. In order to find out H2, we should know T2. In order to find T2, I have used this relation. like how we used for the similar operating condition for a similar problem in the previous class. So now H2 is equal to superheated enthalpy at superheated condition is equal to H2 dash plus Cp of vapor into delta T. Delta T is T2 minus T2 dash. So here Cp have to be found out for the average of T2 and T2 dash, because now we know the value of T2. I want to find out the enthalpy at 2, that is saturated enthalpy plus Cp of vapor into delta T. Delta T is higher temperature T2 minus lower temperature T2 dash. T2 dash is nothing but T3, which is nothing but condenser temperature. Let us move to the next slide. H2 dash is similar to finding S2 dash. S2 dash is vapor entropy. If you see here, S2 dash is this is vapor entropy corresponding to 32 degrees centigrade. So similarly, H2 dash is equal to vapor enthalpy at T2 dash. T2 dash is nothing but 32 degree centigrade from R134A table. So let us take the value from the table. H2 dash is equal to, this is 32, this is like vapor enthalpy 415.9. 415.9. So even though in all the numerical problems which we have solved, there are only few changes. I am in order to make the learners to understand easily, I am solving step by step. Because already we have found the temperature of the superheated vapor at state point 2 is 39.5 degrees centigrade. So even instead of writing directly, I am explaining step by step, so that if somebody has missed the previous lecture, has not referred that one, you can still easily understand. So this is kilojoule per kg. So here H2 dash is found out. T2 dash we know. Cp of vapor we should not take this value, because this Cp of vapor is taken at T2 dash only, not for the average temperature. So this is at this Cp of vapor should not be taken here. So here, since we know this temperature and this temperature, we have to find out Cp of vapor at average temperature. Cp of vapor at T2 plus T2 dash by 2. T2 is, what is the temperature? Temperature T2 is, just now we have found out 39.5. 39.5. T2 dash is condenser temperature 32 divided by 2. So approximately we will get 36 degrees centigrade. So Cp of vapor have to be evaluated at this temperature only. So let me use this space. And if you refer the table at 36 degrees centigrade, this is 36. Cp of vapor is 1.088. 1.088. 1.088 kilojoule per kg Kelvin from R134A table. R134A table. Now Cp of vapor is also found out. H2 dash I have written in the next slide. So therefore, let us take this as equation number 2. Substitute the values of H2 dash, Cp of vapor, T2 dash in equation number 2. We get H2 is equal to, H2 dash we have found here. 415.9, 415.9 plus Cp of vapor is 1.088. That is in the previous slide. Into T2 is 39.5 minus T2 dash is 32. So H2, the value of H2 is 424.06 kilojoule per kg. 424.06 kilojoule per kg. .06 kilojoule per kg. If you see look at the diagram, we have found the enthalpy at 1, enthalpy at 2, enthalpy at 2. Now we will find out the enthalpy at 3, but because this problem involves subcooling, so we have to find out the enthalpy at 3 dash, enthalpy at 3 dash. The enthalpy of the refrigerant after subcooling, that is in the subcooled state. Region which is lying towards the left side of the saturated liquid curve is called subcooled, and the region which is lying towards the right side of the saturated vapor curve is called superheated region. Finding the enthalpy at state point 3 is easier. Directly we can state. Now let us move to state 3. Enthalpy at 3 is equal to liquid enthalpy. So we can write HF3 or HF. Okay. You can write HF3 or HF, which is equal to at T3 temperature. What is the temperature of T3? That is condenser temperature. T3 is nothing but T2 dash, which is nothing but condenser temperature. Equal to T2 dash, which is nothing but condenser temperature, 32 degrees centigrade from R134A table. R134A table. So let us take the value from the table. H3 is equal to corresponding to 32, liquid enthalpy 244.55. To 44.55. So this is what I found here. H3 equal to HF is equal to 244 point. Now we have to find out the enthalpy at 3 dash. Enthalpy at 3 dash. 3 dash, it is not in saturated liquid line. So we cannot take it from the table. We have to calculate. Like how we calculated the superheated enthalpy at superheated condition, we have to determine the enthalpy at subcooled condition. Subcooled condition. Let us recollect the temperature after subcooling is 26. Subcooling is from 32 degrees centigrade condenser temperature to 26 degrees centigrade. So the degree of subcooling is 6 degrees centigrade. So to determine H3 dash, which is enthalpy of refrigerant at subcooled condition. Subcooled condition. So we need to find out the enthalpy of the refrigerant at the subcooled state, at the subcooled condition. Okay, so similar to empirical relation that is used to determine the enthalpy of superheated vapor, I will be writing empirical relation to calculate the enthalpy of refrigerant at subcooled condition. The subcooled enthalpy, that is 3 dash, state 3 dash, H3 dash we need to find. H3 dash is equal to H3 dash is equal to, if you look at the diagram, subcooled enthalpy is equal to saturated enthalpy minus, instead of plus, we have to put minus saturated enthalpy minus preheat capacity of liquid into delta T, So this is equal to H3 minus Cp of liquid. Delta T is, to see the diagram, the degree of subcooling is from T3 to T3 dash. This is delta T. Okay, this is the delta T. T3 minus T3 dash. So T3 minus T3 dash. T3 minus T3 dash. Where Cp of liquid to be evaluated at mean temperature of T3 and T3 dash. Average temperature of T3 and T3 dash by 2. So Cp of liquid have to be found out at the average of these two temperatures. So T3 plus T3 dash by 2 is equal to, T3 is condenser temperature, condenser temperature 32, T3 dash is 26, so the average of that one, 32 plus 26 divided by 2, that is equal to 58 by 2, you will get 29 degrees centigrade. Therefore, Cp of liquid have to be found out for this one. So from R134A table at 29 degrees centigrade, Cp of liquid is equal to 29 degrees centigrade. So we have to take the Cp of liquid. It is 1.442. Let us go to the table. 29 is here. We have got 28 and 30. 28 and 30. So we have to take the average of these two. So this is 28 Cp of liquid, this column. This is the Cp of liquid. And the last column is Cp of vapor. Cp of vapor. So we have got values for even numbers 28, 30. So the estimated temperature is 29. So we need to take the average of these two values. Average of these two values. Let me round off this one. So the average of these two values. Average. Average of these two values have to be taken. So when we calculate it, it comes to 1.442 kilojoule per kg Kelvin. Now I know the Cp of a liquid. H3 is already found. This is H3 already found. So let us take this as equation number 3. Equation number 3. Substitute the values of H3 dash we need to find out H3 dash. Substitute the value of H3. Cp of liquid T3 dash in equation number 3. So equation number 3 is this one. H3 dash, therefore H3 dash is equal to H3 value is 244.55. H3 dash is equal to 244.55 minus Cp of liquid is 1.442. Okay, let me check the Cp value. It is 1.442. The average of the Cp value of 28 degrees centigrade and 30 degrees centigrade. 1.442 into delta T. Delta T is T3 minus T3 dash, that is 32 minus 26. So when we calculate, we get H3 dash is equal to 235.9. 235.9 kilojoule per kg. 235.9 kilojoule per kg. Now, this is nothing but H4 dash. This is nothing but H4. If you look at the pH diagram, 3 to 4 is expansion process, isenthalpic process without subcooling, and 3 dash to 4 dash is isenthalpic process with subcooling. So let me write it here. Process 3 to 4 isenthalpic, that is expansion process, expansion without subcooling, and process 3 dash to 4 dash, expansion with subcooling. That is after subcooling. Okay, with subcooling. So here H3 dash is equal to H4 dash, enthalpy is constant, and in this case H3 is equal to H4. So this should be kept in the mind. So now we have found enthalpy 1, H1, H2, H3 equal to H4, and H3 dash also we have found just now, which is equal to H4 dash. Let us calculate the parameters one by one. So this is equal to H4 dash. First one, we have to find out the evaporator heat load. This is m dot r. Okay, all these are m dot r. So first one is QE. QE is equal to m dot r into. Until now, we have been writing the refrigerating effect is H1 minus H4, that is without subcooling. Now in this problem, since subcooling is considered, the refrigerating effect is H1 to H4 dash. H1 to H4 dash. So this is, so you have to take, this is H4, this is H4 dash, and this is H1. So this is the refrigerating effect. It is not for a problem in which subcooling is involved. Refrigerating effect is not H1 minus H4, it is H1 to H4 dash, H1 minus H4 dash. So if you calculate, we will get mass flow rate is given as 0.05 kg per second, 7.6 kilowatt, 7.6 kilowatt, 7.6 kilowatt. And work of compression, m dot r, compression process is from 1 to 2, so H2 minus H1, H2 minus H1. So let me write the value, because the H1, H2 values are in the previous lecture. Let me write that one. H1 is, I think, 380, the value of H1. H1 is 387.89, 387.89, minus H4 dash is this value, 235.9 into mass flow rate 0.05. So that will give 7.6 kilowatt. 7.6 kilowatt. 7.6 kilowatt. Similarly, m dot r into this one, m dot r is 0.05 into H2 is 424.06, which we have already found. H1 is 387.89. Let us check the value. H2 is 424.06. This is H2, and H1 is 387.89. We will get 1.81 kilowatt. 1.81 kilowatt. Second part of the question, we need to find out the heat rejection, that is condenser heat load, m dot r into H2 minus H3 dash. H2 minus H3 dash. We have to take the state at the end of subcooling. So H2 minus H3 dash. Normally we take H2 minus H3, that is for the condition without subcooling. When subcooling is considered, the enthalpy difference is H2 minus H3 dash, which is equal to 0.05. H2 is 424.06 minus H3 dash is this value 235.90. The condenser heat load comes around 9.41 kilowatts. 9.41 kilowatts. And the COP of the system is the ratio of refrigerating effect to work of compression. Refrigerating effect is 7.6. Work of compression is 1.81. You will get around 4.2. Let us check. COP of the system is, it is 4.2. Let us do the energy balance. Energy balance. QE plus WCO is equal to 7.6 plus 1.81, that is equal to 9.41, which is equal to the condenser heat load. Energy balance is perfect one. Continue in the next lecture. Thank you.